this as well, to provide you with your cell phones and computers. How many elements do you think it takes to make your calculator or your computer or your cell phone? Do you have any guesses out there? 5, 6, 10, 12? Who'll give me 15? Who'll give me 20? 21 elemental constituents to run your cell phone or your computer. None of those are available on any single continent, and none of those are available in the abundance we use them in any single country. Of those 21 elements necessary to run your phone or your computer, in all of North America, Mexico,
Hôm trước
Canada,
mình
United
tới
States,
ta đèo
there are
Este rồi
7
mà phải không?
in the abundance that we are currently using.
Chưa.
In the Russian Federation, there are about 20, 22 of those within its boundaries. Of course, that's 11 time zones, as you recall. China is about 18 within its boundaries, although that's quickly going down to about 16. So every one of us living wherever we are is dependent on other countries to receive the elemental constituents, that is the materials necessary to run our computer, to build our computers or cell phones. So let's think about this for a minute. The magma, I think I'm going to come down, if you'll all bear with me. What we want to do is take those different elements, cool them down enough that they will actually form a rock or a mineral. And different minerals form together eventually to form a rock.
Hôm trước anh không coi được đó, coi đó là rock hả? Trước em coi mà anh không
Nó nói
chịu.
formation, hình như bác có coi mà. Nó nói về vấn đề như là tại sao granite nó form rồi. Bác có coi mà, bác không nhớ hả?
Anh đâu em coi thôi.
Granite nó form rồi cái đá này kia. Nói cái gì excited. Cái đó dở bẹt, cái đó nó dở bẹt. Không hay gì hết.
Instead of that, I want you to think of each of those components as elements. And they're all bubbling around here.
Nhưng mà anh phải mặc 2 quần á, cái được
oxygen bubbling around. And as the magma begins to cool from roughly 1200 degrees Celsius to 2400 degrees Fahrenheit or something like that, the first elements decide to get together. And we get together, but we're very simply bound, and this can be broken fairly easily. However, could I get you to stand up as well? If mineral 2 is getting ready to go, mineral 2 is more complicated. We now have 2 chemical bonds that hold us together. This was mineral 1. This is mineral 2. Now it's much easier to break the chemical bonds with 1 bond than it is with 2. And if I go to the third mineral, we need somebody else, right? And gradually we build till all of us are holding hands, and that's the last mineral to crystallize from the magma. Thank you very much. Thank you. Okay, so that's how we develop the first mineral, and minerals are what make up our rocks. So let's go ahead a little bit and see what we can do about that. So we start with the magma, and the magma, as you can see by the arrow going up here, eventually crystallizes, and we go from 1200 degrees Celsius down eventually to 600 degrees. So the magma is very, very hot. It's hot enough to melt everything. You, the ship, all of the rock that you've seen in the area. So the question is, of course, how do we do that? Because at the surface, that's not taking place. So we're going to have to cool it and crystallize it, and as it crystallizes, it forms the igneous rocks, or the fire rocks, as some people call them. You start with the molten material such as this, and gradually it cools down, and the question is, where did that come from in the first place? So if you look at this diagram, is that visible, going back and forth? This is a different computer. So at areas where the crust is brittle, that is the surface, eventually there are zones of weakness that occur. You'll recall from the first lecture we did, if you have mountain building, you have things that go apart, and you have things that subduct. One of the gentlemen over here, you know, built the mountain for me, the Andes. So these are zones of weakness in the crust, and those zones of weakness which occur at mid-Atlantic ridges, such as you see here, that is, it's opening and magma can come to the surface. And this area over here you have subduction with the denser oceanic plate subducting under the less dense continental plate, and volcanic activity comes up. So these are a couple of ways, or the isolated volcanoes in Hawaii, for example, are ways that magma comes to the surface. And the first mineral we've formed, so what's a mineral? I guess we better know that. An actually occurring inorganic solid or element, compound, having a definite composition, or one that ranges within certain limits, with an orderly internal atomic structure, in other words, crystal structure, that gives it unique physical and chemical properties. And minerals form rocks. So when the first of us got together over here, we just were there alone, but number two mineral came along and suddenly we got together. So we have two different minerals then that formed the rock, the first rocks, right? And as more and more minerals developed, we developed a rock such as this, which is a granite. We'll talk about that in just a minute. But you notice it has feldspar, quartz, and biotite in it. It's not important what the minerals are. There are three different minerals that are involved in putting this rock together. So the typical rocks that form, the first with the simple minerals, are basalt. And basalt is the most common of the igneous rocks at the surface of the planet, including beneath the oceans. Okay? And progressively, as more and more minerals form, instead of being only the early formed minerals which consist mostly of iron and magnesium type of minerals, you begin to get minerals with more and more silica in it, more and more silicon and oxygen. You know it as quartz. And so by the time you get more and more minerals, the mixture of those minerals that come together begins to lighten in color, and eventually you have a granite, such as this. And you can see it's fairly obvious that there's several types of minerals in there. There's some that are grayish, there's some that are very white, there's some that are dark colors, and so on. And all of those eventually crystallized as the magma cooled down to roughly 600 degrees Celsius, roughly 1200 degrees, 1300 degrees Fahrenheit. All right, so now we've got the rock. And the rock is at the surface in the areas that all of us live, and it begins to weather chemically and physically to form sediment. Sediment is sand, pebbles, cobbles, clay, silt, the broken down bits and pieces of rock. Some of those are bits and pieces that you can see, some of those are in solution. And I think the other day we talked about, you've all drunk some water that has a different taste to it, sometimes an iron taste, and you don't chew on iron, it's already dissolved as an element in the water, right? Okay, so as these chemically and physically break down, we then have to do something with them. And one of the things is to go from sand to make it a sandstone, or from something that's a chemical solution, it has to precipitate out, such as limestone, and become limestone. All right, so here's a typical physical weathering. We're going down to an area of the planet where physical weathering is the dominant form of breakdown of rock materials. And you can think about going north into the tropics, it's just the reverse, where you have heat and water you get a lot more chemical activity. You still get some physical, but the dominant force at the tropics, subtropics becomes chemical breakdown of materials. Here's an example of chemical weathering. You can see it's etched out all this light-colored area here, and all of the original rock, which you see here, has gone into solution through chemical breakdown. You've probably all heard of, well, acid rain. Has everyone heard about acid rain, where you have water mixed with carbon dioxide? Carbon dioxide is what we exhale when we breathe, for example. If you combine that with water, you get a very weak acid, carbonic acid, but that over time still eats away at the rock and breaks it down and puts it into solution. So let's look at the whole spectrum here. Here we have the origin of the rock, and weathering is going to take place. And two things will take place. You'll either get grains, that is pebbles, cobbles, maybe even boulders breaking down eventually into sand, silt, and clay, or they will go into solution chemically and form the ions in solution. So each of those then develops, as I said, clay, silt, sand, and gravel. We're going up in size. Silt is like almost like talcum powder, or clay, that size. Sand, I'm sure you've all been walking on the beaches at some point in your life, so you know what that is. And gravel is a mixture of all of these, plus pebbles, cobbles, and that sort of thing that are larger in size. Ultimately, form rocks in the so-called clastic sediments, that is, the broken up bits and pieces of rock here. They form a conglomerate, or sandstone, or siltstone, or shale. You're, I'm sure, familiar with shale and sandstones, and those are known as the clastic rock types. And then the chemically precipitated ones tend to be the carbonites or the evaporites, such as the salt flats that you've seen. All right, so we've got this group of unconsolidated materials here, gravel, sand, silt, and clay, and we're going to have to lithify those somehow. We've got to make them into a rock. So the first thing is you bury them. That is, they more and more pile onto one another. And what would happen if all of the people in the back of the room suddenly stood on the people in front of them? What would happen to you? Nothing? You'd be crushed, right? You'd be crushed, right. So that's the second thing that happens as we get more and more sand or gravel or whatever on top of us, we get compaction of the materials. They are still not cemented together, they're just more compact than they were at the start. And finally, as we have water with dissolved solids in it going in between and among the various pebbles or sand particles or whatever, cementation takes place. So those are the three steps in getting sand or gravels or any unconsolidated material, clay eventually being compressed and then cemented into shales or siltstones or that sort of thing, or sand into sandstone. That's the sequence that takes place. Burial first, compaction, and then cementation. And that leaves us with either sandstones, as you see on the right here, or limestone, the chemical precipitate that you see on the left. So now we have two types of rocks. We have the igneous rocks that form from the molten material. We've broken down that rock that formed, such as a granite or a basalt, and we've broken that into sand or silt or whatever, and we've put some of it into solution. The solution has eventually precipitated out as a limestone, or the sandstone eventually compacted and cemented in place. So the question is, when we have this loose material, how do we get it somewhere else, and what does it do, or what does it matter? So one of the ways we can do that is carry it in rivers. River systems, starting in very high gradient streams, will carry large particles, sometimes the size of boulders. I've been working in front of melting glaciers where boulders twice the size of me, I'm roughly 6 feet, 2 meters roughly, twice my size are simply bouncing down the river. So it's a very high velocity system. It starts bouncing large particles down the river, And if you were to bounce me around enough, I'd break up into pieces. So instead of being a boulder, I'd become a cobble or a pebble. Or maybe I got broken down enough that I'm only sand and being carried by the river down. So in this system, we would be able to carry pretty much boulders the size of double anyone in this room in size. And then we get into less vigorous, lower gradient stream systems, as you can see here. And finally, we go into the really low grade systems. And that water you can see is not clear. It's sort of coffee colored. So it's carrying lots of silt, clay, and at the bottom it's also pushing along sand. All of that eventually gets out to the oceans. And is your beaches. And without breaking down the rocks, there would be no beaches. So here's a typical beach on the east coast of the United States. And one of my colleagues is digging in it. So let's take a close look at that. That's what those sediment layers look like. All of those are roughly the same size sand particles, and they're deposited in summer or in winter. Why the difference? In general, in the northern hemisphere, the winter storms are more significant than the summer storms. So in the summer, the materials are sort of gently brought up onto the land, whereas in the winter, they're tumbled onto the land. So you have two types of sedimentation taking place depending on the storm activity in the region. The same is true in the southern hemisphere, but obviously the seasons are reversed, so the sedimentation is slightly different. So what happens if I can pat that? Lo and behold, I get this. Here's the flat-lying summer layer. Here is the winter layer. Winter layer, flat-lying down here, summer layer. And that's a sedimentary rock, eventually. Here's a sandstone, an example of it. And you can see the various layers here that have been deposited and eventually cemented together. So then we have to talk about metamorphism and metamorphic rocks. How many of you in your distant youth or your current youth or whatever been in a chemistry lab or watched someone blow glass? If I took a rod of glass between my hands like this and did that, it would snap, break in two, right? However, if I put a Bunsen burner or some other flame in the middle of that, I could easily bend it into a different shape. So metamorphism is going to be able to bend rock materials into different shapes. So how do I do that? Where do I get heat? I don't get heat and how much heat do I need? Around 200 degrees Celsius, 200 to 300 degrees Celsius, 400 to 600 degrees roughly Fahrenheit, before I can bend the rock. So I don't get that at the surface, so somehow I've got to get it below the surface to do that. And I can blend it below the surface, but you and I can't see it below the surface, so after it's bent and hardened, I have to bring it up somehow so you can see it up here at the surface, right? All right, so how do I get it down? Pop quiz, you should all be able to answer this. How do we get things down? Subduction, right? Subduction, one goes under the other. So the hard rock goes down under heat and pressure. We get the metamorphic rocks, the third type of rocks that are in the system. So we have to have heat eventually. This means that if it goes very high, 600 Celsius or 11 to 1200 degrees Fahrenheit, I'll be back to the molten material that was the lava where we started out. So where does that take place? These are the general areas of lots of volcanoes and lots of earthquake activity, the red sections here. You notice it's all around the Pacific Rim, the entire area here, Andes up through the Cascades, Sierras, and then out through the Aleutians and down through all of the Pacific Island systems over here. All of those are areas where we have volcanism, so we're bringing magma up from below the surface to the surface. When it's at the surface, it cools and either forms and forms rock again, right? However, adjacent to that, as it comes up, well, I've got a picture to show that in just a minute. The other area, of course, the other areas, of course, where you have instability in the Earth's crust or down the mid-Atlantic region, as North and South America move west and Africa and Europe move east, those are also areas where this activity is taking place. And here's an example of a subduction zone. So you have this cold rock in here, moving down and eventually heating up and eventually melting to form magma. And you have the continental crust moving the other way, so there's a big zone of instability in this area, which permits volcanism, which permits magma to come up to the surface. So that's fine. We now have igneous activity here, molten material coming to the surface, crystallizing into various minerals that form the igneous rocks, such as basalt and granite. What about the area all around here? Metamorphism is taking place adjacent to this. It's in the area that's beginning to cool down, but has not magma that's forced its way to the surface. But all of this zone around here, down in here, along here, and so on, we have lesser temperatures, hence we have the ability to still bend materials, but not break them. Okay? So let's take a look at something like that. Something like this cannot have happened at the surface. I don't think any of you could take a big chunk of rock and bend it like this. This had to have taken place in an area where you had hot temperatures, but not so hot that it would melt the material. This is the sort of thing that we've got our glass blower. It's enough to bend and shape the material, but I don't think any of you have seen a glass blower as they're blowing suddenly have everything melt and dribble onto the floor. Right? So it's an intermediate zone between complete cooling and complete melting. All right, that's at the surface, obviously. You can see some folks there in the illustration. So it didn't happen at the surface, it happened below the surface, so how did it get up to the top? Absolutely right. Down here she's going, right. Subduction is going, if I were subducting under all of you, the entire auditorium would gradually rise. And the further I would go under you, the higher you would get. So if you were, here's the surface, here's the intermediate zone that's been bent and folded, here's the zone down here that's completely melted. I'm bringing you to the surface, the middle zone is going higher and higher and finally is up near the surface. And then I have to get rid of what's on top of you. And I do that by chemical and physical breakdown of the materials that are on top of you, so that all of the top area up there is gone and the bottom area of the auditorium here is what I see. At first, all I saw was the three people in the back row. Back row got rid. We got rid of the second back row and so on down. And finally, the only thing that was left was this gentleman down at the bottom. Everything else has been taken away by chemical and physical activity and moved from wherever it was, by landslides, by glaciers, by river water,
Mình đâu có biết nó chỗ nào.
to the sea, to the ocean, where it's deposited and it's okay. So here's a typical gneiss. This is a metamorphic rock. What rock do you think that came from? What igneous rock do you think that might have come from?
Quartz.
Quartz. Well, that's good. Quartz, but with other minerals, would be a granite. Quartz is one of the principal minerals that make up the granite. In other words, this didn't come from a basalt. You'll recall that the salt was a dark black rock, much of which is at the surface and we'll see. But yes, this came from this rock. And you can see all we've done, excuse me, all we've done is taken the original minerals that you see in the granite over here, put them in some degree of heat, not enough to melt them, but I can stretch them out. Because remember, to do metamorphic rock, I have to have temperatures around 200 to 300 degrees Celsius, 300 to 400 degrees Fahrenheit, something in that range. And we're bending things, but if I'm bending you, you aren't going to be sitting the way you are. If I were to bend you or even ask you to all lean to the left, I don't think any of you are going to be actors. I just can't have it here. But as you lean to the left, we've changed your shape. You're no longer sitting like a nice human being like this. You're starting to stretch out to one side or the other. And that's what's happening to these minerals. The granite, the minerals of the granite, the black, which are obvious over here, have been stretched out into lines. That's happened beneath the surface. If you see it at the surface, which we see metamorphic rocks at the surface, it's because they started down here and were lifted up, and then whatever was on top of them eroded away and exposed them. You know, sort of like right now you're all dressed up. If I want to see what you're really made of, I've got to get your clothes off and have you in swimming suits, and suddenly I see what's underneath. Your skin underneath instead of all your clothes covering you up. And I've seen some of you out of the swimming pool, so what we're doing basically is you've eroded the top layer by taking off your clothes and putting on your swimsuit, and all I see is your, whatever's exposed with your swimsuit on, right? So it's very similar to what's happening here, except obviously one's rock and one isn't. Okay. So what we've done is what I've tried to do is take you
I know
through,
some very loud noise below
take you through
my
what is
floor.
known as the
I
rock
on
cycle.
10,
We start
but
with
below
night
about
one.
9. I
We
think
cool the
somebody
temperature
hit
from
something
the 1200
to
Celsius
continuously
to
about
20
10 or more
Fahrenheit,
than 10 minutes. I don't know,
gradually
something wrong
cooling
there?
it, stratifying it,
Come in?
solidifying it
The
to
noise.
igneous rock down at
They
around
hit
600
the
degrees
wall or
Celsius.
hit the
And the
floor or
last
something.
mineral to crystallize, last common mineral to crystallize
Yeah, they hit
is
very
quartz.
loud. Very loud, I don't
So we
know
go
what
from
reason.
producing dark
Okay.
colored minerals down here, principally involved in the combination of iron, magnesium type elements with silica and oxygen, to something at the end of the spectrum which is virtually only silica and oxygen, which you'll recall from the first or second slide are the two most abundant elements in the planet, in the Earth system. And so they're the last ones remaining. Everybody else has been used up. So you get the igneous rock, and it weathers either chemically or physically. And that breaks down into sediment, boulders, cobbles, pebbles, sand, silt, clay, or chemically into ions that are dissolved in the water. And that then gives us the option of taking these dissolved solids, precipitating them to form the sedimentary rock you probably know as limestone, or perhaps dolomite. If you're from Europe, the Dolomites of Italy, for example, are made up of dolomite, which is a calcium magnesium carbonate, as opposed to straight limestone, which is just calcium carbonate. Or you end up having sandstone after you've compressed the sand and cemented it together, or perhaps slate, where you've taken clay and compressed it and cemented it together. All of those rocks then have to be broken down to form sediment, which we just did, and are lithified to form the sedimentary rocks. All three types of rocks, the fire rocks from the molten material, the igneous rocks, the basalts, the granites, as well as all of the sedimentary rocks, sandstone, limestone, shales, that sort of thing, and all the metamorphic rocks, the granites, the schists, the marble, limestone, heated up slightly becomes marble, for example. All of those are at the surface and have to be broken down to repeat the cycle. But if I take them all the way down by subduction into the interior of the Earth, and I'm talking 5 to 30 kilometers below the surface, they will all go back to being the magma. Molten material with all the elemental constituents bubbling around like a big bowl of vegetable soup. Only in this case, it's a big bowl of elemental soups. And that takes you back to the magma. So in this brief talk, I hope I've given you an idea of where all of your rocks came from, or come from, depending on their age. But a geologic age is a different thing. I sometimes use the entire width of the stage to show how insignificant we are. Some of the rocks, the oldest on the planet, we're going to start with 0 over here, and we'll call it a 24-hour day. And over there is 2 minutes ago. So here we are in a 24-hour day, and the first and oldest rocks that we have on the planet, located in parts of Australia, northern Canada, parts of Africa, and so on. There are a number of places. Continue along until about, let's say, 9 o'clock at night. We're about 3.5 billion years ago. We haven't even begun to be thought about. First single-celled critters. Some of the algae are here. So let's see, we're about halfway through our 4.6 billion year history, and we begin somewhere around noon. You've had breakfast. It's noon or somewhere around that time. We begin to see more fossil evidence beginning to be there, mostly of the invertebrates. The mammals haven't shown up yet. Nothing much happened until about 600 million years ago, which is around here. We've got about 3 hours left in the day. 9 o'clock at night now, 2100 as opposed to, we started out at roughly 0900, 1200, and 1300, 1 o'clock. Okay, so here it's about 2100 in the evening. Do I have any fisher people in the, fishermen, fisherwomen in the audience? Anybody? Oh, I've got a few. You would have been in seventh heaven, sir. Because this is the age when we had massive amounts of fish species on the planet. More than any other thing on the planet were fish. But of course, unfortunately, I don't think you were living 300 million years ago, were you, sir? Okay. So we keep going along here. Let's see, I'm going to write out quickly. 2 million years ago, we've just begun to be somebody, right? But 2 million years on a 24-hour clock puts us at about 11:55. 23:55, okay? And when we get right up to the wall here, you're at 23:59 and a half. And that's about when we really became a dominant form on the planet. And if we look at the paint, I'm sorry, this doesn't have paint on it, but you get the idea. We started despoiling this Earth at 3/1000ths of a second of a 24-hour day. That's how significant we are. So I think it's always important to recognize geologic time as much more than we think about in the clock on the wall. Right? The rock cycle has been going all of that time. And as a result, the rocks you see and the rocks you walk over are somewhere in that spectrum. Now, where we've been down the coast of South America and where we're going to the Antarctic, none of them are the ancient of ancient rocks. The Andes only formed somewhere about started to form somewhere about 130 million years ago. Any of you who were on excursions yesterday, you were going over the debris from the Andes that had been dropped down toward the sea. In fact, it was underwater until very recently from a geologic standpoint in time. And you've been walking over stuff that's very, very recent. And until we get down to Ushuaia and Punta Arenas, where the Andes come back in, you will not be seeing or have been on very old rock. But in both those places you'll be in, well, there are areas in both of those places where you could be on much older rock, as opposed to something that's very, very recent. Okay, thank you very much for attending. I hope I've given you some idea of how this all fits together. I'll be up in the Gaspé Lounge in about 5 minutes by the time I get this taken down. See you there if you have any questions. Thanks very much.
Good morning.